Okay, so welcome to this week's CFA colloquium. My name is Karin Öberg. I'm here to introduce this week's speaker, Rob Garrod. So Rob Garrod is an assistant professor at the University of Virginia. Before joining the faculty there, he was a postdoc at Cornell and a Humboldt Fellow in Bonn. Since his early postdoc years, he has been a leader in astrochemistry, and especially in the theory of how larger, more complex molecules form under the from a chemist's point of view, very strange environments that's present when stars and planets are forming. So without more ado, Rob, please.
Okay. All right. Well, thank you very much, Karen. Thanks for the invitation. I guess everyone can hear me, right? Yes. Okay. 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 I'll speak as loudly as I can. Okay. So if maybe you were here at lunchtime, I was talking then briefly about simple molecules, and I'll speak a little bit about those as we go along, with a particular emphasis of this talk, and I would say a major emphasis of what we do in my research group is to look at the production of some of the most complex molecules that we detect in the interstellar medium, in particular in star-forming regions. I should say that I'm a member of the astronomy and chemistry departments at UVA, and that's actually a fairly good description of what I do. It's a pretty much a 50-50 mix of the two, but I should say that pretty much all of the stuff I do is computational. So where you see any observational results that I'm presenting, I take no credit at all for those, and I'll tell you who to credit as we go along. So molecules are actually fairly ubiquitous in the galaxy. I'm sure you recognize this kind of an image looking toward the Galactic Center, and so obviously we see a lot of brightness there that is stars, but there's this dark foreground material that is interstellar clouds, and in fact the darkening is caused by the dust in those clouds. So this is an interplanetary dust grain. So somewhat similar to interstellar grains, about an order of magnitude smaller typically. So these interplanetary dust grains that you can pick up in the stratosphere with airplanes, there may be on the order of a micron or so in size. In the interstellar medium, we think on average we're talking about, say, 0.1 microns, something like that. But it's not just dust that is there, but it is ices that form on their surfaces. Again, I showed this picture earlier, but this is this 2 to 20 micron wave band where you can detect infrared absorption from, in particular, simple hydrides, other simple molecules, CO, CO2, but there are very strong features from water, because you can see the silicates as well. That's evidence of the actual dust grains themselves. So we can identify a certain limited number, maybe a dozen or something like this, of these simple molecules in the solid phase, but in fact most of the molecular material that we detect is found in the gas phase. Okay, so this is again, not my image here, but this is a pretty well-known galactic survey of CO, and in fact it's not quite the same scale, but you can see in this sort of central region here, you're tracking the same sort of material, and a lot of these same features start to become apparent. So these gas phase molecules actually trace quite nicely these dark, dusty interstellar cloud regions. So let me say something about the chemistry then, in a very sort of simple, generic sense. There is a lot of gas phase chemistry going on in the ISM. This doesn't cover everything, but a lot of the chemistry is driven by ionization. So we'll have ion-neutral reactions. Those go faster and usually a little bit more efficiently than neutral-neutral processes. But the ionization itself comes ultimately from cosmic rays. Okay, so these are high energy charged particles that typically will collide with H2, which which is the major component of the dense region, these dense interstellar clouds. And these ions, sort of this ionization passes through gradually through the chemistry and allows a more complex chemical composition to evolve. The temperatures, though, are very low. And from the point of view of the chemistry, that means that only certain reactions will tend to be important. That is to say, exothermic reactions, typically those that don't have barriers. Okay, so most of the chemistry is driven by these barrierless processes, and in fact, these ion molecule reactions are often exactly that. They are barrierless and exothermic. The pressures, though, are low too, and what that means for the chemistry is often the changes that we might expect over time will take a very long time to take place. So maybe thousands of years for things to change noticeably. We also don't have three-body processes. That's important maybe for those of you who might be chemists who maybe see three-body processes more commonly in the lab. This is not something that tends to be prevalent in the ISM. We never really see thermodynamic equilibrium at all in the chemistry, save maybe for a few examples. And that means that we need kinetics. So in other words, we need to study the rates of chemical reactions to understand the chemistry. We can't just take some equilibrium chemistry approach to understand interstellar molecular abundances. So that's a gas phase chemistry. I will mention, and of course you'll probably be sick of it by the end of it, but I will talk about here the surface chemistry that goes on the dust grains that I've mentioned turns out to be very, very important, not just for the simple molecules, but actually for the really complex molecules that I, in particular, am particularly excited about. So this is a fairly typical list of the molecules that have been detected in the ISM. There's something like 200 of them so far. They're being detected at a rate of about 3 or 4 per year. And it's been that way. It's been a fairly steady increase since about the 1960s when these microwave detectors became sort of more generally available. So most of the molecular material, of course, is H2. Only about 1 part in 10,000 is not H2. I should point out there are certain definitions that we like to use. So in astronomy, we'll often talk about complex molecules as being molecules that are composed of 6 or more atoms. So I will stick to that convention. So if I mention the word complex, that's sort of the right-hand side of this table that I'm talking about. But we further define what we call complex organic molecules, or COMs. You may see me using the shorthand somewhere along the line. And so again, it's these very complex but carbon-bearing molecules. And often, a lot of these COMs are actually molecules that you can buy in a bottle. They're sort of fairly familiar from a high school chemistry lab. We do see them in interstellar space. Often their abundances are somewhere on this order, so maybe 10 to the minus 8 with respect to hydrogen. They vary a bit, but that's a good number to hold in your head as a typical abundance in star-forming regions, at least, for these more complex molecules. So the formation of these things, well, we see diatomics and triatomics actually in many regions, starting with diffuse clouds. So they, at least these diatomics in particular, are able to survive to moderate abundances in even fairly diffuse regions where there's a lot of UV invisible that could otherwise break them apart. When you want to go to somewhat more complex species, though, you have to typically look toward these dark, dense regions. This is Barnard 68 as an example. But they're well protected from external UV by the dust that is sort of permeating these clouds, and that protects these molecules from dissociation by UV invisible light. When you want to go to the very complex molecules, though, we almost uniquely go to look in star formation regions. Okay, I will exclude maybe a few of these molecules. So Brett, you have to keep your mouth shut here. But for the most part, most of these complex organics are found peculiarly in these molecular clouds where stars are forming. Okay, so there's something unique about the star formation process that leads to this very complex chemistry. So I will introduce what is certainly the richest source of complex organics in our galaxy, Sagittarius B2. So this is a sort of a long wavelength radio image toward the Galactic Center, and we're looking at this thing, Sagittarius B2. In particular, there is a core within that called Sagittarius B2 North, and this really is the richest sort of star-forming source. And so we give these chemical-rich star-forming sources a particular name. We call them hot cores. They're hot in the sense of they have excitation temperatures, molecular excitation temperatures of about 100 Kelvin, or typically somewhat more than that, and they're also cores. The spectra, though, are incredibly rich. So this is actually an old spectrum that my colleague Arnaud Beloche took using the IRAM 30-meter telescopes. This is a single-dish observation. What you see here is towards Sag B2n, this broadband spectrum, and then above this zoomed in little sort of portion here with lines all the way through. Okay, and almost every feature here is an actual emission line from a molecule. So most of this is not signal to noise. It's not noise here. They are actually features from molecules. So they're incredibly complex. Only something like 50% of the lines that are generally observed, certainly in Sag B2n, are actually known features from known molecules. So we don't have the spectroscopy for a lot of these features to identify particular molecular carriers. Okay? It's likely that a lot of them are actually produced by known molecules, but in higher vibrational states that we don't have the spectroscopy for from the lab. But there's a lot, as you can see, a lot of sort of molecular information, as well as being a lot of molecules. So molecules that we particularly associate with hot cores, we often just call them hot core molecules, but that would include alcohols, aldehydes, or at least aldehyde groups, ethers, esters, and we have these nitriles or cyanides here that turn out to be very abundant as well, not just in this source, but in star-forming regions in general. And I'll sort of talk a bit about their chemistry in a few minutes. First, though, I wanted to actually highlight a molecule that I was involved in detecting, or at least part of this this group that we established. So I spent a couple of years in Germany at the Max Planck Institute for Radio Astronomy, and this collaboration grew, at least from my point of view, from that. So we detected this molecule, which is called ethyl formate. We put out a paper about it. In fact, we were very excited because this was, at the time, one of the most complex molecules that had been detected in any star-forming region. In fact, I presented this work at a conference in the UK, and we got some press interest. Not, unfortunately, for the things that we were excited about, but in fact, because this is actually an ester that is implicated in the flavor or the smell of raspberries and rum. Okay? Now, I'm not sufficiently expert in either of these things to really vouch for the truth of that, but I think it is sort of, as I say, it's not uniquely implicated, but it is one of many components. But anyway, the press picked up on this little discovery, so we made it onto The Guardian. So The Guardian is one of the more sober publications in the UK. The Sun is somewhat less sober. But so this was 2009. This was coming up on 10 years ago, right? So that was the end of the story, right? Or so I thought. So coming up on a year ago, I guess, I got an email from the BBC asking me again about this story. And so, I answered their questions and I thought, okay, fine. But the next day I was thinking, well, I wonder what it is that spurred them to be so interested in this story. And a few weeks later, I figured out, or at least I think this is the reason why they picked it up. So I was sitting at home watching a movie on a Sunday evening, sitting there with the wife. We got towards the end of the movie, so this is Molly's Game. I don't know if you've seen that. It's actually not a bad movie. And right in the last 5 minutes of the movie, Molly walks in and says, the center of the galaxy is ethyl formate, which is the same gas that gives rum its smell. And then she says, it smells like rum and raspberries. And you can see how excited he is about this revelation. But anyway, I think the BBC got this news from watching Hollywood movies. Anyway, so I think this is probably the first and last example of astrochemistry in the movies. I guess we'll see. Time will tell. Okay, so... but yeah, so this is all sort of very silly stuff, right? But the bigger picture that maybe doesn't keep us awake at night, but occasionally sort of, we're sort of inspired by, is this question of where these very complex molecules fit in this whole process of star and planet formation. This, again, not my picture, but this is a sort of pretty well-known image. If you imagine you start off with some sort of diffuse or dense region, and then somewhere in that cloud you will form some core, some dense region that ultimately will collapse down and form a star. And then ultimately you'll produce your disk, and planets will come about from this process. Well, the objects that I'm talking about, we're detecting complex organics here. Okay, so this is not a system or an object where we have even planets formed yet. We don't have any sort of solid bodies formed. This is still the very early stages of star formation, and yet we're detecting these very complex organics. So it raises the question, at least, I don't think I'll be answering it today, but it raises the question, do we actually seed these planetary systems for life at their very inception? Right? So that's the kind of question that we have in the back of our minds, at least. The questions I'm hoping to answer as we go along here with my models is, firstly, how do these molecules form? How complex can they get? And I'll give a particular example at least. And can we use them to understand other properties of star-forming objects? So not just to study them for their own interest, which is fine for me, but I think there is actually some value in studying these molecules from the point of view of pure astronomy. So what is the recipe for these complex organics? I'm going to cut out an enormous amount of my field here, completely dismiss it, and say that we think, in general at least, gas phase mechanisms are not responsible for producing these large, highly saturated organics, at least these aliphatic ones, these sort of chain molecules rather than aromatic species or whatever it may be. Okay, so as I say, I'm being somewhat unfair, and I think there are certainly examples where these large molecules could plausibly be formed through gas phase mechanisms, but as a general rule, I don't think that's true. In fact, I think there's a lot of evidence now that the answer to the production of molecules like this raspberry and rum molecule involves ice on dust grain surfaces. Okay, so we've seen this little video before. I'll just turn it on again. But the idea here, and so this is a sort of a simulation of a very simplistic dust grain, really just to show you now what we think is going on to form these ices on the grains. So we have hydrogen diffusing around on the surface. There is oxygen that is that is accreted from the gas phase onto the grain. The same for the hydrogen. The hydrogen is actually quite mobile and can move around, and when it meets oxygen, when multiple hydrogens meet multiple oxygens, we end up forming mostly water and a few other things as well, at least in this network. So this is a pure hydrogen and oxygen network that we have in this model, and we can form several molecular products that end up forming these rather larger ice structures on the grain surface. So here the camera is sort of pulled back to take this large molecular structure into account. The size of the grain itself is something like this underneath, in this simulation at least. The blue here, I should point out, is molecular hydrogen. It's formed on that surface, but it gets stuck in these little cracks and crevices in the ice. So there is trapping of even quite volatile molecules in these irregular ice structures. So this was a preliminary model from, I guess 6 years ago, goodness. We've done a somewhat more complex model now. So this is still looking at an interstellar grain. The grain is still ridiculously spherical, but it is at least amorphous in terms of its microscopic structure. So we have an irregular surface structure for that grain that is nominally made of amorphous carbon. It's a bigger grain as well. And we have a bigger chemical network. So we have hydrogen, carbon, oxygen, nitrogen, and then CO accreting from the grains. And then if we do these simulations, this is a much faster simulation than the other one, but it's taking probably, I don't know, about 100,000 years, something in model time, to produce these large, sort of fluffy ices on the grains. Again, these are formed by chemical processes on the surfaces. I want to point out one particular reaction process that involves this thing, methanol. Okay? And the reason is, and I'm sure many of you will be familiar with this idea, but there's a lot of CO in the gas phase, and that CO can stick to the grains. But when it does so, it can react with this very abundant atomic hydrogen, and it can be repetitively hydrogenated all the way to the simplest alcohol, methanol. In fact, we detect methanol in infrared absorption studies. In the ISM, it can have abundances as high as maybe 30% in some sources, 30% of the total fraction of ice. But this molecule actually turns out to be very important for the production of more complex molecules. It actually acts as the feedstock for these larger species, as I'll show you. So we can form these simple species, but the question is, how do we go from the very simple ones that are mainly formed by hydrogen addition to something more complex? And the answer seems to be this energetic processing that comes from cosmic rays. So is this constant flux of high energy particles, and they're able actually to penetrate even the deepest, darkest regions of star formation where just a UV photon could not. Okay, so what we think happens is, I mentioned that ionization is caused in these clouds by cosmic rays. The process is as follows. So a cosmic ray comes and bumps into H2, and it can ionize it, but it can also excite it. Okay, and when it's excited, it can gradually decay through its electronic levels and produce a UV field. Okay, so the cosmic rays penetrate the cloud, but then their interaction with H2 produces a local, weak UV field within the cloud. Okay, you can actually ionize the H2 as well, and the secondary electron that comes off will go bumping around, exciting other H2 molecules, and again will produce this UV field. This itself is not new. Okay, so this idea has been around for several decades. What we've been doing over the, let's say, past decade, though, is to consider what happens when this UV field impinges on these dust grain surface ices. Okay, one of the effects that we would expect to see is that water, which is still a primary component of these ices, can be dissociated by a UV photon into an OH group and an H group. Okay? But also this methanol that I mentioned we form through hydrogen addition can be broken up into several reactive radicals or functional groups. And those functional groups can then react with each other very quickly if they're able to meet. And that is we think the sort of the real trick or the unique point that is associated with star formation here that produces these very complex molecules. So the picture we have in general, okay, so we form ices at low temperatures through diffusion. We produce radicals through that mechanism I mentioned, UV dissociation. But the warm temperatures that are associated with the star formation process, the warm-up of this envelope of material, gradually heats the grains as well. Okay, and when that happens, the radicals that you produce in the ice or on the surface of the ice start to become mobile on their own. And then they can meet, and then they can form these larger species. And ultimately, as temperatures really increase to sort of the typical observed temperatures of 100 Kelvin or so, you start to see these molecules come off. So ultimately, the entire grain mantle desorbs thermally, and all this stuff that you produced in the grains or on the grains is now observable in the gas phase, okay, observable through primarily rotational transitions. Okay. So the thing about methanol, if we're looking at sort of typical hot core molecules, so these are just 4 of the more typically observed ones, maybe not glycolaldehyde, it's a little bit harder to detect, but certainly methyl formate, dimethyl ether, and to some extent ethanol, all detected commonly in hot cores, and we can produce all of them by this combination of photofragments from UV photons impinging on these interstellar ices, these simple ices. All right, so I will make one final point, which we'll come to at the end, which is that it's not just formation that is affected by the cosmic rays. It's actually destruction of gas phase molecules can be caused by cosmic ray ionization as well. Okay, so I'll mention a couple of things then. Firstly, I'll talk about some work we did observationally and some work in particular that I did to try to understand those observations. So this is work led by Arnaud Beloche, but including myself, Holger Müller in Cologne, and Carl Menton also at the Max Planck Institute for Radio Astronomy. So this is an ALMA project called EMoCA, or Exploring Molecular Complexity with ALMA. So we were looking at Sagittarius B2, this really rich source, and we detected a lot of molecules. Okay, the one I'm going to talk about in particular is this one. This is actually the first publication we got out of this work. So let's take a look at this Sagittarius B2N source. Well, firstly, just looking at the structure of it. So historically, with lower resolution observations, you would see just a sort of a blob for this north core. We can actually resolve not just the 2 cores that we actually sort of thought were there based on the line profiles, but 3 new hot cores, N3, N4, N5. Okay, so this is not just now one star-forming source, high-mass star-forming source. It's actually 5, and now we can resolve them all. Okay, now here we're going to concentrate on N2. N2 is the second strongest source here, but turns out for various reasons to be a little bit easier to identify molecules in its spectra. So what did we find? Well, the big news was we found this thing, isopropyl cyanide. Okay, we'd already detected its sibling here, normal propyl cyanide. What was exciting about it, though, it's a different structure, okay, but it's the first detection of a branched carbon chain molecule. Okay, the detection was pretty safe. Okay, so usually we think of maybe a dozen lines from an individual molecule as being a good detection. Here we found 50 for this one, so we're absolutely certain it's there. What was really sort of, I guess I should say, interesting here was not just that it was detected, though, but that it was detected in significant abundance. So it was about 40% the abundance of its normal form, its straight chain sister, if you like. So, okay, so what does this all matter, right? I mean, it's a new molecule. Well, it is a new class of molecules. There hadn't been any previous detections of this kind of branched aliphatic species. But it was also not present in the chemical models. That's to some extent why it was so surprising. We really had no idea how abundant it should be, or even whether it would be there or not. In a larger context, I guess, we're interested in this detection because this branch structure is important, or is certainly a feature of amino acids on Earth or in meteorites, right? They have this side chain structure. So now we're seeing that we can form that kind of structure in the interstellar medium as well. Perhaps not a big surprise if you're a chemist, but nevertheless it is there. But the question, though, is how is it formed? And can we, in fact, reproduce its abundance in the ISM? And to do that, we have to study kinetics, and we have to use, well, a rather more complicated model than the sort of the one with the videos that I just showed you. We need a large chemical reaction network. We need to be able to produce this molecule, and the way we sort of tend to assume it's formed would be in the solid phase or in the ices through these radical reactions. But we also need to include destruction mechanisms as well. Okay, so this is the model I use. It does certainly look less sophisticated than those videos. It is unfortunately not possible at present to do that kind of modeling for chemical networks that are this complicated, but also for objects that have such complicated physical structures. We have to go back to a somewhat simpler method of modeling. So we model just the populations of each chemical species, not the actual microscopic physical positions on the grains and so on. Okay, this model has a full gas phase chemistry, but it does still have the full grain surface chemistry and actually a mantle chemistry, so we can have UV photons going deep into the ices and inducing chemistry. But more or less, it's the same type of chemistry as we saw in the other model. It's based around this idea of diffusion on surfaces or even in the bulk, driving the rates of reaction. When things meet that are reactive through diffusion, then they can react where they are. Okay, so in these models, we have a lot of differential equations. That's what we're actually solving. To give you some perspective, we're typically talking about hundreds, in this case 700 or so unique chemical species. More if you include, if you sort of treat each phase separately. Thousands of reactions, again, typically more than 10,000 or so. Some networks are even bigger than that. But these are sort of, these are substantial chemical networks. There's a lot of detail we have to think about. But I will spare you all of that detail. And I will go straight to some results. Okay, so observations showed us this 0.4 ratio. We did models, and in fact, we got pretty close. We got a ratio of 2.2. Okay, that was our best model, or closest one. In fact, so what that's telling us is that this branched molecule is more abundant than the straight chain form in our simulations. The results I'll show you here just for give you an idea of what's going on. So we've got time going on here. And then at the same time, the temperature of this hot core, the star-forming region, is gradually increasing. Around 100 Kelvin, these ices, which are the dotted lines, desorb from the grains and are available in the gas phase to be detected. Okay, so we see our propyl cyanides here, our iso, which is a bit more abundant than the normal straight chain form, a little bit lower. So I did a lot of models. In fact, I tried many, many different things to try to reproduce this ratio, but I couldn't do it. Okay, there was something missing, apparently, in the chemistry. Everything I tried, we always had this overabundance of the branched form. So we went a little bit further, and I'm not sure how we're doing for time. Okay. So we went a little bit further, and this was a piece of work that was published in 2017, I guess now. So we went a little bit deeper into the chemistry, not only of the propyl cyanides that we detected, but actually we threw in the next largest homologue. So in other words, the same class of molecule, but with this extra methyl group included. So whereas we have this normal form and an iso-branched form for propyl cyanide, actually we have 4 different forms for butyl. So we've got the straight chain form N-butyl cyanide. We've got 2 singly branched forms, iso and sec. And then we've got this tert form that is doubly branched, if you like. It's this kind of cross shape. And then we threw in some other pentanes just because we didn't think the network was complicated enough already. Okay, so for the butyl cyanides, I'm not going to go through all of this stuff, but I'm just pointing out here that these were the reactions that I included for each of these 4 different structures of butyl cyanide, but they're mostly radical reactions. So the dot here is an unpaired electron. That's what a radical means. It's one of these sort of functional group species that has an unpaired electron. It's very reactive and should react without a barrier. Most likely will form a stable product when we're looking at reactions on grained surfaces. So most of these reactions are like that. But in fact, even this on its own was not enough to turn around this sort of discrepancy between models and observations. What I had to include was a different type of reaction. Okay, and this is, I promise, the last bit of chemistry I will show you. This was a set of reactions that involve this cyanide group, which again is a radical, inserting itself into an unsaturated hydrocarbon. So in other words, it's a hydrocarbon that has a double bond. That CN radical attacks the double bond. And that's important because we can form immediately a precursor radical for propyl cyanide in this case, or butyl cyanide in this case, a precursor radical that has the cyanide group on the end. It's that straight chain form that we weren't producing enough of before. Okay, so we do that, we add a hydrogen in our network, and we form N-propyl cyanide and N-butyl cyanide. Okay, so without these without these actual additional reactions, then the branching dominates the chemistry. I should say these are not sort of arbitrarily defined by me. They've actually been investigated, at least in the gas phase, and they've been found to go without a barrier. So we should expect them to go on grains in the ISM. Okay, so what do we see as an actual model result here? So firstly, we reproduce the observations. We get greater abundance of this straight chain form than the iso form. As I said, this was the only process that I could find that would actually reverse that ratio. So we're already looking at a success, I guess you could say, based on that new set of reactions. But we went further. We wanted to know, actually, could we predict the presence of butyl cyanide? What we find, actually, even in this case, even with this new mechanism, the straight chain form is less abundant than the branched form. Okay, so we're seeing sec dominates. So it seems as though, as we go up in complexity, the probability of finding these branched molecules really starts to ramp up. Okay, it's possible actually that the sec form is detectable. I'll say something briefly about that in a minute. The tert form, unfortunately, this doubly branched form, almost certainly not detectable. It's a good couple of orders of magnitude below the most abundant one, so it's probably not going to be detected anytime soon. Okay, so that was a particular example about molecules, and I just wanted to round out what I'm going to say. Just to say something about a project a student of mine is doing where I think we're really starting to harness this kind of chemistry to say something useful about physical conditions in star-forming regions. So this picture I showed you simplistically has a couple of major parameters that we haven't really constrained very well. Okay, and that's true, I'd say, in all of these models, whether it's me running the models or anyone else. Firstly, we don't really know what the cosmic ray ionization rate should be in any individual region. And in fact, even in a general sense, there's a wide divergence in the estimates for that rate. And secondly, we don't have a very good handle on what this warm-up timescale is, the speed at which the temperatures increase during star formation for an individual parcel of gas is not very well described by theory. So hopefully we want to try and use comparison with observations to constrain both of these. Okay, so this is sort of a little bit of context here. I mentioned that we ionize H2 with cosmic rays, and that produces H2+. Okay, that is the main source of ionization in interstellar clouds. Okay, the rate is typically assumed to be about 10 to the minus 17. That's what we often claim is the canonical rate. It's only really determined in diffuse gas, though. And in fact, it can vary by orders of magnitude depending on who you ask, depending on what they measured. Okay, it's not very well defined at all. We know from what I just said that the cosmic ray ionization rate is directly tied to the production of complex organics on grains, but we also know that it's directly tied to the destruction of those molecules later in the gas phase. So hopefully there is some happy medium that we can tune to in our models to reproduce observations. Okay, so that's what we did. So my student, Chris Barger, ran a grid of models, 9 models in time, 9 models in cosmic ray ionization rate. They're all more or less varying by a factor of 2 between each model. And we run 81 models just to see what happens. Okay, so these are the sort of results for some of the common hot core molecules. Okay, so we're seeing cosmic ray flux increasing from left to right. The warm-up timescale, this sort of characteristic chemical timescale, increasing from top to bottom. Okay, so if you look at the bottom right here, we've got a very high fluence of cosmic rays over that full time period. The chemistry really doesn't look very good. It doesn't look very much like what we'd expect. It's a terrible mess, and everything is generally not very abundant. Okay, so we can pretty much rule that extreme case out. But pretty much all of these other combinations are not so bad, depending on what physical conditions we're looking at, so what the physical spatial structure of a particular source would be. Okay, so we have to go a little bit beyond just modeling chemistry, but actually try to put the physical spatial arrangement of these molecules into our treatment as well. So this sort of simple method that we use. We basically take a generic model that we ran out of that grid, and we map it on to a temperature profile that is observed. Okay, so you can take dust temperature profiles from the literature. These were profiles that Floris van der Tak obtained nearly 20 years ago, I guess. But in his work, he has a temperature profile for a particular hot core and a density profile. Okay, so we map the temperature structure of the molecules onto that profile, and that gives us everything we need to actually simulate the emission from those molecules and therefore simulate the entire process of observing that source. Okay, so we can fold into that the convolution of the emission with the telescope beam. We get a full spectrum for all these molecules that we're interested in. And then we can directly compare the integrated intensities of the emission lines themselves with observed values. Okay, so we're essentially creating an entire simulated spectrum and comparing it with the observations for particular sources. So we looked at 4 particular sources, 4 commonly sort of observed hot core sources. What did we find? Okay, well, we have a method to sort of assess how closely the models match the observations, but this is what this is showing. So if you look at the sort of the redder, the hotter parts of these diagrams, they're showing you the model that best fits the observations based on the integrated intensities of all the lines of all these molecules. We had to throw a few out because we knew from the beginning that their chemical behavior was not really going to match the observations in any way. That I think we sort of understand what the underlying chemical issues are there, but we threw them out for that reason. But it's based on these 10 molecules. So what we see, in fact, is that firstly we can fairly uniquely pick out regions, this one maybe not quite so much, but generally pick out a fairly unique region of parameter space that best matches observations. But this tells us a pattern. There are some clear patterns here. One is that the optimal cosmic ray ionization rates that we get from this analysis are uniformly higher than the canonical value. Okay? Often maybe as much as an order of magnitude higher, or for W33A, a little bit higher than that even. Okay, so we're looking at actually quite high values, more than we would have expected. The other side of things, though, is the best warm-up timescale or characteristic timescale for this process is actually faster than the fastest timescale that we use generally in any of these models. Okay, so we're actually looking at quite an extreme outcome from this comparison with observations. Now, I was sort of excited about this finding, and I talking to my student, I said, well, there's just a couple of things we could do to really check out whether this is realistic. And so the first thing I did is ask him to compare the cosmic ray ionization rate we get with the column density of the gas in this hot core, because we can get that from these observational density profiles. So we can calculate that very easily. What we see, it's only a statistical sample of 4, but we do see a relationship here. So we see that the higher the column density, the lower the ionization rate. And that scales with what we would expect. We would think that gradually these cosmic ray, the cosmic rays will lose energy as they go deeper and deeper into the cloud. So it's not doing something that we wouldn't expect. Okay, so that's already good. The other thing I asked him to do, though, was to check the correlation between this warm-up timescale and the integrated mass of the hot core. So in other words, the total mass that we have in the star-forming core, and compare it with how long it should take for this material to warm up. Again, we find something that is in line with what, at least qualitatively, we would expect, which is that the more massive sources are going to evolve more rapidly. In fact, we get a very nice correlation, again, only 4 points, but it's a nice correlation between these two. I will point out there is work done on this through other methods, okay, and these are some recent simulations that Marco Padovani did, looking precisely at the drop-off in cosmic ray ionization rate with penetration into in this case, a quiescent cloud. In fact, our data are a little higher than theirs, but considering there is some uncertainty in this fit, I think it's sort of consistent, at least with their upper limit. So their upper limit is these, this is high and this is low. Okay, so we're sort of consistent with their upper limit, but if this is real, if we really are a little higher than what they find, this may actually be telling us that there is some other source of ionization in these star-forming regions. Perhaps there is some internal protostellar source of ionizing high-energy particles. And that's something that other people are putting forward. That's certainly not my suggestion, but it seems to be in line with that idea. Okay, so what comes next? Well, a sort of final slide to tell you what's coming in the future. And there's a few things we're doing, but one of the things that is most exciting for me is that we got some money from NASA recently to combine proper MHD simulations of star formation with the kind of chemical and spectral modeling that we've been doing. So these are results from a sort of preliminary model that we put in the proposal, but we're currently doing one-dimensional MHD calculations just to get things rolling, but the focus of this is going to be 2D and ultimately 3D simulations. And by doing that, we'll get not just a sort of a mapping effect of mapping the chemistry to the physical structure, but tracing the chemistry as that physical structure changes and doing it in a physically consistent and defensible way. Okay, and ultimately we can get sort of spectral simulations. We can produce these full spectral full spectra and compare them directly with observations, and do all the sort of things that we would do usually for an observation, but we can do it with our simulations. Okay, so that's something I'm very excited about. So I will just reiterate what I've been sort of talking about, which is, I mean, the main point here, I think, is, you know, this branched molecule doesn't look like much, but it really does open up a whole new frontier in this kind of astrochemistry. I mean, I have to say, from my own point of view, it loads me up with an enormous amount of work, because now we've got to start thinking about branched versions of all these molecules that we've detected. So there's a lot to think about there. We do think that the more complex the molecule, the more likely it is to be branched. I guess that's sort of obvious as a chemist. But it's likely also that, you know, these cyanide molecules, these nitrile molecules that I was showing you simulations of, may be unusual in having that special mechanism that tends to favor this straight chain molecule production. You know, most other molecules that don't have this nitrile group probably don't have mechanisms like that, so they may show even more branching than the nitriles that we've detected so far. The other thing I want to stress again is, you know, often we give these talks and say, look at this molecule, and this, isn't it exciting? And maybe the chemists say, yes, that's very interesting. But the astronomers say, what does it do for us, right? And, you know, I think to some extent, we overlook, by concentrating on individual molecules, we overlook the statistical information that these broadband spectral observations can give us, can actually feed into the models to help us tease out this kind of physical information, you know, this warm-up in this case and cosmic ray ionization. But I'm sure we can find ways of exploring other parameters using the full degree of complex molecule information that we get from these observations. Okay, so I will say thank you, and if you get bored of my thanks, you can look at the videos. So I will firstly thank the EMoCA team, the observers and spectroscopists that I work with. There wouldn't be much point in doing the models without. I will thank my group, not individually, but there they are. And I will thank NASA for throwing money at my program. Thank you very much, NASA. And thank you all for listening. Thank you.
I was thinking of more complex molecules and what the status of the observational search for them and the theoretical limits and things that can be placed, like, for example, the purines and pyrimidines of the nucleotides, adenine, guanine, and so forth. There must be some work done in that on their presence in outer space.
Yeah, I mean, there's lab work done, certainly. So there's ice experiments done where they irradiate the, you know, sort of mixed ices. I think spectrally detecting those kinds of molecules is going to be very difficult. I think in an object like Sgr B2, you know, we're essentially at the limit of what we can detect now. We have essentially perfect spectra with ALMA. And we're not going to detect. I mean, this is something that, you know, we've actually got new data for Sgr B2 to redo this ALMA survey that I mentioned, and we find N2, at least at core N2, we don't see a great deal of new information versus what we already had. You know, I think you know, if we can find sources that have very, very narrow lines compared to what we're looking at, so that may be low mass sources, perhaps looking in particular points in space, you know, we may be able to find richer spectra. But I'm not sure. I mean, it's sort of hit and miss for any of these molecules. It's sort of blind luck to some extent. But I think, you know, those really, really complex molecules, you know, I'm not sure we're going to see anything anytime soon. But you know.
I heard, but haven't seen the article that they discovered something like 35 lines of a very complicated, very close to a purine or pyrimidine in outer space very recently. You haven't heard about that?
I don't know. Yeah, I'm not sure.
I think it was still a precursor, so pretty far removed from these more complex molecules. So it was more of the same size. But I think the talk showed it was the same thing.
So you know it was...
I think it's fine, yeah. Okay, let's start there.
Yeah, I have a question since you already gave a talk in the afternoon on this on the lunch, during the lunch. So from the naive perspective, the efficiency of formation of complex molecules should scale as metallicity to the power of heavy atoms in it. Is that right? Because basically you do it one by one, and concentration goes as metallicity, proportional to the metallicity on the first order of magnitude.
Yes, I suppose.
Because then, if you go to low metallicity region, at some point you'll reach the moment when you simply don't have enough time to form those molecules before the formation of first massive star, which will destroy all this molecular kitchen by the UV.
Well, that in itself is an argument. I'm not necessarily going to accept that suggestion. Well, because for one thing, I mean, we have there's still an open question as to where cometary material comes from. You know, there's a lot of complex material in comets. It's not clear whether that material is actually natively interstellar or whether it's formed in protoplanetary disks, for example. So I'm not sure we're quite at the stage to say that. Let me see. Sorry, what was the first part of the question?
So the first part is that since the efficiency goes as number of atoms to the power, metallicity to the power of number of atoms.
So there have now been observations of these kinds of complex organics in the Magellanic Clouds. The metallicities there are, I don't know, a factor of a few lower or something like that.
2.
Yeah. And, you know, our models of at least the simple chemistry seem to produce an explanation for example, why there's not very much CO, ice, so solid-phase CO, and I think the small Magellanic Cloud, I don't think there's any detected. But nevertheless, you know, you are seeing complex organics in the Magellanic Clouds, and apparently with high excitation temperatures. So, I mean, I don't think having a somewhat lower metallicity at least rules out the production of complex organics.
Gary?
Just a comment and a quick question. The cosmic ray ionization rates that you seem to require seem to be well within the range of the cosmic ray ionization rates that were inferred from Herschel measurements. Mm-hmm. This is this PRISMUS program that Mary von Garrod led and David Neufeld was very active in. So I wouldn't adopt the tone that this seems out of bounds of what expectations are, because I think it's well within the range of what they've measured.
That is true. The issue, though, is that those are, I think, exclusively determined for diffuse regions. And
they are, yeah.
And what we're determining through this sort of indirect method is getting the active cosmic ray ionization rate in the very densest, darkest regions of these objects. And, you know, there is an expectation that those rates drop off in those dense regions.
Yeah, I forget the highest density regions that they probe, but generally, yeah, you're right. The quick question I had is, do you see a utility in correlating the strength of a CN stretch feature in the ice? I think it's at 4.27 microns, which can be quite strong toward a lot of sources, and these more complex molecules and their branching ratio.
It's hard to say. I mean, I would think that unless you can identify a feature that is uniquely not associated with HCN or whatever, then you know, I don't think you'll be able to say.
I think it's denoted XCN,
yes,
which is just the CN stretch.
That's still
mainly OCN, though.
It's OCN, right?
Yeah.
Okay, yeah.
Well, but we have data on that towards just a handful of these kind of sources. So actually, Rob and I have sort of tried to do something like this, but the statistics is not there right now. So having more statistics, I think, would be useful, even just for the precursor material.
Yeah, I mean, it would be useful.
We'll get potentially millions of them with spherics.
I was trying to
Okay.
encourage.
I wasn't leading you there necessarily, but I just was wondering about whether you saw the utility in trying to correlate.
Yeah, if you're able to find it, then yeah, by all means, it can be factored into these simulations.
Alyssa.
I almost don't dare ask this because this is already so complicated and impressive, but have you considered, if you said, these grains are so spherical, and basically I'm going to ask you about polarization. And so the actual solid material, the ice, is your little spherical blob, which hardly matters when you have this giant layer of ice on it for what the final shape of the grain is. But when you take the ice off the grain, then you get back to the actual shape of the grain. So if the grain is elongated, then you get more polarization, right? So I'm just wondering if you look for this desorption in places where you also have polarization information, if there's too much confounding stuff going on, or if you could actually just say, if you have more polarization, you have less ice, and that the chemistry is or isn't consistent with that.
It's a good idea. I don't know. I mean, I've been setting up these models in such a way that we can investigate different shapes of the underlying grains. I mean, yeah, my feeling is it probably won't make much difference to have a somewhat, sorry. Yeah, exactly.
Right.
Exactly. So yeah, it's a good suggestion, but I'm not sufficiently competent as an observer to really tell you whether that is plausible or not. I don't know.
So have you investigated what if you use silicates, for example, instead of amorphous composites? If you were to do them on like a composition of dust that you think is out there, X amount of silicon, X amount of carbon, X amount of oxygen, like does that affect the chemistry significantly?
Yeah, I think it would affect it at the higher temperatures when you don't have much ice. I mean, as soon as you've built up a monolayer of water, it's not really going to make much difference. But it's a valid question, and it's something I hope, again, not just the morphologies of these grains, but the composition, I hope we can sort of investigate a bit more. To do that, of course, we have to start producing our model grains in a more realistic way, and that is something, again, that I've started doing. You have to use the proper amorphous carbon potentials, and you can do the same thing for silicates. But then you've got to get into the molecular dynamics. But maybe sort of a few years down the line, we may be able to say something on that.
Well, with that, I think let's thank Rob again.